To see if we can get this whole picture to hold together, then what we need to do is begin to think very seriously now about the mathematics involved underneath. So we will be discussing in depth now the math of wave packets. This wave type idea that maybe, if we think of how the waves behave in time, can reconcile those two pictures. Now, let's just begin with a basic review or overview of how we construct a wave packet and how we describe them. So the basic idea, as you may recall, in calculating brightnesses, because it's really the brightness that we calculate, and that then tells us the probability of where these events are going to occur. You may recall that the basic strategy for that, particularly when you were doing like a multi-slit experiment type analysis, what you would do is you would take all of these phase factors, e to the I kx, where x was the distance traveled from your various slits, right? And you would add them all up. So eventually there's going to be some kind of an integral here. It could be a continuous integral or a discrete sum, depending, was it a finite slit you might recall, or a sum over a series of discrete slits. And the point was, though, that this here described the phase for you. Then what you did is you added up all of those different phase factors. And what that gave you then was the amplitude of the wave, a complex amplitude. And the amplitude function in quantum mechanics we usually call psi, right? Sometimes called the wave function. And for us, this will depend, because we're thinking about how packets will move in time. This will ultimately depend upon time. Amplitude is what it's called in classical physics. It's generally called the wave function in quantum mechanics. So I'll label it like so, wave function for quantum mechanics. Its amplitude for, basic in your basic course on waves. But now the brightness, you might recall, B of x, that you would calculate from the amplitude in order to get the brightness, or it's sometimes called the intensity. To get the intensity, you will recall you always had to take your amplitude, and then after you had done this geometric series, the sum over all the slits, you had to take the square of it, the complex magnitude squared. And remember, our theory is actually that the brightness is proportional to the probabilities. So after we do this calculation to get these probabilities, this is the one thing we can know. We can't know where they will show up. We can know the probabilities, and we can calculate them. And the way we calculate them is we are saying they are proportional to the brightness that we expect, which we then are equating to our amplitude squared using the wave physics part. And so this amplitude squared must then be proportional to the probability of finding the particle at location x at our particular time t. Now, this is the description that you have, of course, if you are just thinking about a standard interference pattern where you're not worrying about how the interference pattern might change in time, right? So you should also recall that when we look at waves and how they depend upon time t, there's also always this minus omega. And leave a little space here. Something's going to come in a moment, but minus omega t, like so. And the reason why we write things this way is that you will recall, to describe waves as they change in time, you will recall, Euler's formula, which tells us that, in fact, e to the I theta has this cosine part and this sine part. Now, if we look, for instance, we can look at either part. They pretty much do the same thing. But if we look at the cosine part of this, we would have a function, something like cosine of kx minus omega t. And of course, what that is describing then is a nice, up and down cosine type wave. And what the minus omega t thing is doing is having these wave peaks move along at some speed. Now, there is a bit of a potential problem here. And that is, you'll notice that this wave, okay, it has its peaks and valleys, right? But when we square it, it'll all be peaks, right? But the main thing, though, is it isn't localized anywhere, right? It spreads all over the place. It isn't like compactified into a wave packet yet. And the way we do that, the way we build it into a wave packet, is we actually have to superpose multiple waves, each with their own weight. So there's generally in this function, there's also a weight function that we include, W of k. These would then be the weights for the different waves. So that's describing the weights. This thing, this part here is describing the various waves. And of course, we're doing superposition, and that's why we're adding them up, right? That's why there's an integral here, with a dk function there. Now, the last little thing, just to remind you and why we left this little space, is you will recall that wavelengths of a wave vector k, waves of a wave vector k have different frequencies omega. So omega in general is a function of k, and that functional form also has a relation. While we're reviewing everything, this has a name. It's called the dispersion relation. So that's our basic setup for how we could construct a wave packet. The last little ingredient is to understand a little bit about the structure of what these weights here are going to look like. So for the weights, the first thing I want you to notice is that these weights themselves in general are complex numbers, just like our waves here are just being described in the complex representation. And these complex numbers, like any complex number, can be written as an amplitude, right, or a magnitude, which I will call A of k. And also, they in general can carry a phase, right? And that phase we represent by a complex exponential again, e, and usually it's written I times some phase, which I will call phi, which then could depend upon k, like so. Now, just to make the math work out a little bit later, I'm going to anticipate a little bit. I'm just going to define this particular phi for these weights actually as a minus of itself, right? But, this is just the minus of the normal phi that you would normally expect. Now, just again, since we're talking about complex numbers and doing a little bit of review, we can show you what this W of k would look like in the complex plane, right? It's just a complex number. So it's going to have an imaginary part, which we usually put on the vertical axis, and a real part that we put on the real axis. And this A of k then is telling me the amplitude, or the length, of the vector in the complex plane. So in general, it'll be some point in the complex plane. It's useful to think of it as a vector, which goes from the origin to that point in the complex plane. And the length of my vector here is A of k. And then the angle, the direction of the vector, is determined by the angle with respect to the real axis. Normally it's measured upward in the positive direction from the real axis, but in this case I just happen to write it with a minus sign, so actually this angle here, phi, this angle here would correspond to whatever phi that I'm putting up there. Now, the last feature of these W's that's important to understand if you want to make a wave packet that is actually localized somewhere, if you want it localized somewhere and you want it to be moving, right, then what you want to do is you want to make this amplitude have a very particular feature, and that is that amplitude should be, relatively small in most places, but then have a peak somewhere. And I'm writing this as a function of k. And if you don't want the thing moving, you would center the peak around k equals 0, right? But if you want it moving, you would center it around a particular value of k, and I will just call that value k0. That's the value where I'm going to kind of concentrate my amplitude. And my claim now is if you put all of this mathematics together for this type of an amplitude and phase factors to build up these weights and combine them with your waves and integrate up to add all the waves together, you will indeed get an amplitude function psi that moves around like a packet, and then we can begin to understand its physics and to see what we need to do to make it line up with our expectations of classical physics to make up the correspondence principle. Now, the last little detail I want to say before we begin to think about that more complicated mathematics is, of course, the picture I've written down for you here is what the motion would look like in one dimension. Later on, you'll see if we want to go to higher dimensions, things generalize pretty naturally, and most of the key ideas that we really need to understand are uncovered by the mathematics that I'm describing for you here.